All right, our next piece we'll look at the Ethernet networking. Um, so kind of a difference from where we left off with the serial networking. We looked at serial networks being a lot of times daisy chain and linear type trunk topology. Those two topologies are actually supported in Ethernet networking as well. We could do a daisy chain approach from device to device to device, assuming that each device kind of has two ports. You could actually daisy chain. And trunk line, there is an older kind of precedent on Ethernet to kind of use coax, and you could kind of create that trunk and tap off the trunks. But in most modern topologies, shall we say, that we see on the plant floor, more specifically, typically boils down to either star topology or a ring topology. So those two examples are shown right here on the slide. So the topology on the left is a star topology, and it's called that because it kind of looks like a star. And usually what happens in a star topology is you have a switch, and then you have a run from the switch to each device. So in this case, we've got 6 laptops and a switch. So we would need to have a switch that has at least 6 ports on it so that we can connect each laptop to a separate, unique port. The topology on the right is a ring topology. And in this case, each little square in that ring would be a switch or some kind of tap, perhaps. And off of that device in the ring, the switch, you would go off to a device such as a computer or a server. So the advantage of a ring topology is that it can survive it can tolerate a single point of failure. So in a ring topology, if we had a break in the ring somewhere, then it would self-heal and kind of go the opposite direction around. So for instance, if I had these two computers down here, if there was some kind of break in the network at this segment in the ring, then the ring would be still valid from here all the way to here. So this computer and this computer would still be connected. At that point, it becomes a linear flat topology. All right. Now, if I had a break here and the ring kind of healed itself, and if I had another break here, well, it's not going to survive that because now we've isolated these 3 by themselves, and we've isolated these 4 things by itself. So we have a break here, and we have a break here. So that's where the ring will kind of fall down. So we can tolerate a single point of failure, but we cannot tolerate 2. In a star topology, we don't quite have the issue of where if I have a break, I'll lose the whole network. But if I had a segment failure, such as this cord here going to this computer, well, we lose that computer, but everything else is still working. But if I were to lose the switch, if the switch here in the middle fails, well, then obviously all of this stuff doesn't connect or communicate anymore to each other. If I had a switch failure here, well, all these other devices are still working fine, right? I'm only going to really lose this computer off the ring versus everything on the ring. So rings are very popular for resiliency. The term is resiliency. Stars are easy to implement, but again, there's perhaps some risk there based on a point of failure here with that switch. So one thing is, you can also have mixed topologies in your network. So we're not really limited to just saying, okay, it's going to only be a ring, it's only going to be a star. And then in this diagram, we actually show 3 topology types, all all in one network. We have a linear network over here, and then we've got a star topology here, and then we have a ring topology up here. So this kind of looks to be like the central hub, right? So we have all of our computers starred off here. Then we have a star topology going into a ring topology here. And then we kind of got our star topology going into a ring topology here. Should have said a linear topology here, I believe, and then a ring topology up there. So we can definitely mix and match our topologies, which is another reason why Ethernet had become, or has become, very popular network of choice for industrial automation and plant floors, because in the past with the serial networks, in addition to being limited to speed and distance and the number of devices, here you also had the limitation of the topology, right? It was either going to be a daisy chain type network or a trunk line type topology. Now we have the flexibility with Ethernet to mix and match topologies based on pieces of our plant. So looking back at this diagram again, we showed this in the introduction video, and we said that it looked like a lot to try to decipher at that point in time. So a couple of things to note about this drawing, or this diagram. The red box is typically what we as OT people, and again, remember OT stood for operational technology people. So for those of us who are responsible for maintaining the control systems and the automation and all the stuff on the plant floor, we kind of fall inside that red box. So those are the cell area zones of the plant floor. The layers above it would be site operations, which could be something we get involved in. So that would be your, back to your control room levels. And then above that is the industrial DMZ and the enterprise zone layers 4 and 5. So the enterprise layer, of course, would be what we see our IT people really kind of own. And the concept of the industrial demilitarized zone, or the IDMZ, is simply that's kind of a buffer area between the enterprise level and the plant floor. And the point of that is with cybersecurity, of course, being top of mind, we just can't put our plant data out there on the internet and have the enterprise just kind of go grab it off the internet. We want to do things in a bit of a secure manner. So we want to really protect our plant floor from intrusions and denial of service type attacks, right? We don't want people to shut us down. Same time, we don't want to, give entrance into the enterprise system, right? We don't want people hacking into our corporate IT side and then stealing whatever our, Coca-Cola secret formula or our personal, personnel data and stuff like that. So the IDMZ is a bit of a buffer zone to kind of prevent, rogue access between the layers. So again, we're going to really focus on what's inside the red box. And what's inside the red box are 3 different cells, as we'll call them. So that could be 3 different units within the plant. And each one of those cells is arranged in a different topology. The one here on the far left is a star topology. We have a switch and we have star type topology going to our devices. The one in the middle is a ring topology, right? We have our switch, and then we have a ring going around, and then we have a bunch of devices kind of tapped off the ring. And we do show some kind of mixed topology here, right? We do show a star topology off this switch, which is in turn tied to that switch, which is in turn on the ring. And our last cell area is a linear network. So we just kind of come in with a switch. We're just kind of doing a flat linear approach across the switch, across the cell. Simple architecture. Okay, so each one of those blue squares are basically Cisco symbols for various components, be it a switch, an access level switch, or a larger distribution level switch. And we'll show that on another slide. All right, so a common thing to kind of get to understand at least it's kind of difference between a hub and a switch. To some extent, they're the same, but in many ways, they're totally different. So a hub is simply a place where you're just going to plug a bunch of things in. There's really no security to it, and there's really no kind of control of anything. It's just very much like a it's like a central gathering point of all this stuff. So what I'm trying to get there is that if PC4 is going to try to communicate to PC5, well, whatever it sends out through the hub, it's going to send it out on every one of these ports, because it doesn't even know what port PC5 is even connected into. It just knows that, hey, I'm looking for PC5. So it sends the request up into the hub, and the hub says, we don't know, shoot it out every port. So every port on that hub, that one, that one, that one, that one, that one, it will shoot the message out on, and hopefully it'll find its intended target. A switch is different in that it's a managed product. It's a managed switch. It actually has a computer chip on board that controls all this stuff. So now if PC4 is tied to a managed switch and it wants to talk to PC5, it's already mapped in the network, and it knows that PC5 is on port 5. So the packet comes out of PC4, goes into the switch. The switch says, yep, I know where PC5 is. It's out that port right there. And it sends the packet out that port. It never blasts it out the other ports. So it's a much more optimized way of handling your traffic. So on an industrial plant floor, we like that. We like things to be optimized and controlled. We don't like the shotgun approach that a hub would have, because if our PLC is trying to talk to an I/O product out there on the plant floor, we don't want to have to blast out that command to everybody and everything on the plant floor. We would like to target that message exactly to its intended destination as quickly and seamlessly as possible. So for that reason, we always prefer to use a switch on the plant floor and not a hub. So industrial network switches, just some examples. These are Rockwell products, the Stratix line as they call them. It should be noted that many people make industrial switches nowadays. Pretty much every major manufacturer, Siemens, and Rockwell, of course, and then a bunch of kind of other brands you've probably never heard of before, companies like Moxa, Hirschman, Intron. So there's a lot of people that make industrial switches. What makes an industrial switch different than, say, what you would find at Delgado's in their IT room is that these guys are industrial in nature. So they're designed to be rugged. They're designed to be on the plant floor. They're designed to take the heat and the vibration of the plant floor. So they will work at a extended temperature range, typically from minus 20 degrees Celsius to 70 degrees Celsius. So that's a pretty wide temperature range. If you try to take an industrial, a non-industrial switch and put it on the plant floor, it's not going to survive. And if you ever go into a computer room, typically the AC is blasting in those rooms to keep things cool. And we know that on the plant floor, things aren't always going to be air conditioned. So there are three types of switches typically. For the most part, we're going to just kind of boil it down to this. Far left is an unmanaged switch. So the unmanaged switch would work very much like the hub explanation I gave there a moment ago. So they don't have any intelligence to them. They're not managed. So just a simple hub or a simple switch. Whatever goes in packet 1 or port 1 is going to get shot out on all the ports. The middle guy is an access switch. They'll call it access switch, and that is a managed switch. So that is the one that can learn what's plugged into it and can make the tables and essentially know how to route the traffic to the right spot. Access switches are basically the guys you would see on the plant floor at the cell zone area down at the equipment. The distribution switch, so you can see it's a different package. It's actually a 19-inch rack mount guy. It is a managed switch, of course. So what makes distribution switches different is that they're designed to be at those higher levels in that organization chart we showed a few moments ago. So kind of in that plant level range, or even up in the enterprise level range. So the idea is that your access switches would be kind of the guys closest to the equipment, gather in all the stuff on the plant floor, and they will actually talk up to a distribution switch, and a distribution switch will actually kind of connect various other units within the plant, or maybe even different buildings in the plant, and then bring that up to the higher levels in the organization. So you wouldn't necessarily put a access level switch up there at the higher levels. You'd put a distribution switch in those layers. So just a few more points to always make you aware of these terms, right? So managed switch and unmanaged switch. So so managed switches, again, of course, they are more expensive, and they do require more work of support and configuration to get them started. So there's a lot of setup involved in it. But the advantages are there's all the managed features, such as you can create VLANs or virtual LANs. You get a lot of diagnostic information. You have a lot of security built into it. You get a lot of prioritization with quality of service, QoS, meaning quality of service. You get some better network resiliency capabilities and loop preventions, which are very important, because you can take your entire network down if somebody were to kind of create a loop inadvertently on the network. Unmanaged switches. So the biggest advantage of an unmanaged switch is really that it's a lower cost, and they're very simple, and they're good for small and maybe isolated networks. So if you're just trying to put a small system together in a panel and you don't really need to worry about connecting to other things, sure, an unmanaged switch would be ideal for that. The disadvantages, of course, is doesn't have any of the managed capabilities, so we don't have any of the security built in. We don't have any of the other managed features. Don't get a whole lot of diagnostic information out of it, so a little bit harder to troubleshoot perhaps. No resiliency support and no loop prevention, which is probably one of the biggest issues. So if somebody were to create a loop on that unmanaged switch, you could literally bury your entire network by doing so. The bottom one is embedded switches. So that's chart. This chart came from a Rockwell slide that I found, but embedded switches so some products actually have the switch embedded inside of them. Some Ethernet cards, especially in a PLC. So that's what an embedded switch would actually refer to. So here are the icons we talked about a few moments ago. So this slide will be posted as a PDF, and it's a good reference. So if you see all these blue boxes and you get a diagram one day, and again, this is Cisco uses these diagrams, but I know a lot of other people probably use something very similar. So this is not part of the ISA standards for P&ID diagrams. These are more networking things. But if you do see a networking diagram one day, then perhaps this will help you decipher some of that. So the top left there, you see layer 2 access switch, layer 2 industrial Ethernet switch. So if you see the little IES anywhere, that stands for industrial Ethernet switch. So those little products we showed a minute ago on that slide, those switches, that would actually be the box we would see used a lot there. As we kind of move down, we see multi-layer switches and layer 3 core switches, and those are getting into the higher levels of our network distribution and core switches. You see the little disk at the bottom of the left, layer 3 routers. So if you had a router, they look like little hockey pucks perhaps. So a router is a little different than a switch, but the router is actually going to allow us to connect different networks together. And we'll kind of discuss that here in a moment. Right hand side just shows some other things such as firewalls. So everyone could be somewhat at least familiar with the concept of a firewall. There are firewall hardware products, so there's always a firewall in your computer, but there's also industrial firewalls or hardware appliances, firewall appliances, that can be installed in the network that would also prevent network intrusions. So again, now based on that, we kind of know how to decipher this diagram a little better, right? So when we saw down here in our cells, we see the IES. So we got an industrial Ethernet switch here and here, and industrial Ethernet switches here and here. And then as we go up here, we're getting more to our distribution switches, and then up here to our core switches, and on up in the enterprise, additional core switches and routers and whatnot. So you can kind of go back and look at the previous slide and get all your feel for all these diagrams, or these little icons, I should say, and come back to this diagram and kind of just be able to figure out what the pieces of the puzzle are to kind of put this network together. All right, so let's talk about some additional Ethernet concepts, or industrial or Ethernet, I should say, Ethernet concepts. So first is the idea of a MAC address. So MAC address stands for Media Access Control Address, or MAC, for the acronym there. So the MAC address, so every device that has a network card on a network interface on it is going to have a MAC address, and every device out there is going to have a unique MAC address. So think about that for a minute. Every computer that has an Ethernet card or port on the computer has a unique MAC address. Every PLC with an Ethernet port on board has a unique MAC address. Everything in your house that has Ethernet on board it, such as your Xbox, your TV, smart TVs, they all have MAC addresses. So just think about the number of devices that you might have or know of alone, and multiply that by the number of people in the world and the number of industrial facilities in the world, and that is a very large number of MAC addresses out there. So essentially the MAC address, it's manufactured into every network card, such as Ethernet cards or Wi-Fi cards, and they cannot be changed. So the MAC address is actually set by the manufacturer, and the MAC address is typically it's got six two-digit hexadecimal numbers separated by colons. So for instance, you'll see there in a little box on the right, we got a MAC address of 00. So it would actually be read as 00:1A:3F: F1:4C:C6. And again, that's hexadecimal numbers. So if you haven't learned hexadecimal numbers, go ahead and take the time to Google that at one point, and you'll kind of learn hexadecimal is a base 16 number system used very commonly in computers. So usually the higher bytes, may not be the right term, but the higher side of the address is the organizational identifier, and the lower side of the address is the actual kind of unique interface. So for instance, Rockwell Automation would have its own unique organization identifier in the MAC address. GE would have theirs. Whoever makes the NIC card for the Dell computer would have their own. So that way you would know just on the MAC address who was the original manufacturer of it. And then of course the numbers that was shown here in the blue boxes would be the actual kind of like a serial number, shall we say, or the unique identifier for that from that manufacturer. Now, we don't normally worry about MAC address in our day-to-day life. Occasionally, we do need to kind of know MAC address, but for the most part, we're going to be working with IP addresses, or Internet Protocol address. And the IP address is the address used in order to uniquely identify a device on an IP network. The address is made up of 32 bits, which can be divisible into a network portion and host portion with the help of a subnet mask. And we'll talk about the subnet mask in a moment. So, so these 32 bits are broken into 4 octets, as they're known. One octet is 8 bits, octet 8. And then, since nobody really knows how to decipher a binary number easily, we always refer to our IP addresses in a decimal
format and usually separated by a period or a dot. So for this reason, IP addresses always have to be expressed in the dotted decimal form, such as we see in the example on the right, 192.168.100.1, or I should say 192.168.100.1. And then the value of each octet can be anywhere from 0 to 255. And if you go 2 to the 8th power, you'll find that it's actually 256, but we start with 0 in the computer world, so therefore it's 0 to 255. So our biggest address that we can have in each one of those octets is 255. So 192.168.100.255 would be the largest address on that particular IP range. Now, a common question is, what's the difference? Why don't we just use MAC address? Why do we have to have a MAC address and an IP address? And what's the difference? So the big difference is that MAC addresses are used to ensure the physical address of the computer, and the IP address is the logical address of the computer device. The MAC address operates in the data link layer, and we're going to talk about layers. There's going to be a module on layers, OSI layers coming up for you to read over. That makes a little more sense at that point. The IP address is in the network layer. The MAC address is really to identify the device itself, whereas the IP address identifies the connection of the device on the network. And the biggest difference, or the biggest issue, I guess, with the MAC address is that you cannot change the MAC address, but you can change the IP address. Okay, so again, MAC address is the kind of the address of the computer itself. It becomes that physical address of the computer, whereas IP address is a logical address. So we can control that. If we want to organize our computers or our PLCs in a logical group, therefore the IP addresses, right? We can say, we're going to have a group of IP addresses between 192.168.1, and go from like .1 to .10. That's a logical grouping. And that's a lot easier to understand than trying to take all these various MAC addresses, which are going to be all over the place, to try to manage. So another thing to kind of just discuss here is the concept of static versus dynamic IP addresses. So in a static IP address, we're going to basically hard code an IP address into the device itself. So we, as the end user, be it engineering or IT, we're going to actually give it an IP address. And that IP address does not change unless we manually change it. And the difference with dynamic IP address is that dynamic is changes just by the name, as name implies. And for instance, our laptop, if you take your laptop to your house and you hook into your Wi-Fi, you don't set an IP address ever. The Wi-Fi router will assign an IP address to your laptop. That is what's known as DHCP, or Dynamic Host Configuration Protocol. So the router itself will dynamically assign a IP address to your laptop. So today, you come home, your laptop might be 192.168.1.22. Then you come back home tomorrow, your IP address might be .28. It can be something totally different than it was yesterday. And every time you reboot your computer or recycle power, then possibly that IP address could change. So on the plant floor, that is not a good thing. We do not want to have all of our IP addresses just dynamically changing at undetermined times. So if we're trying to make things talk to each other, we have to know their addresses, and they should not be changing. So for that reason, static IP addresses are
typically preferred, and I say typically just because there's always people who do things a little bit different, but quite honestly is always the preferred method for industrial networking applications. So let's look at that maybe in this topology, right? So here's a simple star topology of a little industrial control system, right? So we got a switch in the middle, IES, and its address is 192.168.1.100. And then tied to that switch, again in a star topology, we got a operator interface, we got a PLC, we got an I/O drop, we got a drive, and we also have some kind of a server, say an HMI server. And each one of these guys has their address assigned to them, right? So the operator interface is .21, the PLC is .11, I/O is .12, drives .13, etc. So the PLC is going to want to talk to the I/O, and it's going to want to talk to the drive. So if the IP addresses were always changing, the PLC has no idea, has no way to determine that. So usually what we do is we tell the PLC, hey, I got a drive out there, and that drive's at address .13, and it makes the connection, and they start talking. If that .13 goes away, then it doesn't talk to it anymore, right? It can't find it. So it's going to be a communication error on the network. I went ahead and did a ring topology architecture as an example, just to show you how that might look as well. So now we have the ring, and we have 4 switches on the ring, and each one of these switches, we have our devices tied to those switches, and then therefore they get into the ring. So in this example, the ring would definitely be a more complicated thing to try to manage, right? We've got 4 switches as opposed to the previous diagram when we had 1. And we have so much more expense as far as hardware goes, and we have a lot more time to kind of configure 4 versus 1. But the advantage of this architecture, again, like we said back in the topology discussion, was this is a more resilient network, in that we could tolerate a single point of failure in the ring, and it's still going to keep running. So that is worth the extra work there, perhaps, if it keeps your plant running during a single point of failure. So another concept to kind of discuss real quick is subnet mask. So all this time we've been talking about a simple IP address network of 192.168.1, and then that last octet, 4th octet, we always were changing the number because that was going to be the actual kind of address of the device itself. That is what's known as a Class C subnet or Class C network. And that's what we're most commonly seeing. And what we mean by subnet is that we're masking out basically the first 3 octets. So our network, all of our devices in our network, if the subnet class is C, they all have to have the 192.168.1 as the first 3 octets to be kind of considered to be on the network together. So if I came in with my laptop and I chose a totally different octet, like say the first octet, say I went with 193.168.1 something, I'm not going to be able to see anything in the 192.168.1 subnet. So that's kind of what that is trying to imply there. So you can kind of see there's also a Class A and a Class B. In the chart on the side there kind of shows you some of the things that happens, right? So if we're in a Class C network, which is the red box, 255.255.255.0, then we have a total available 256 addresses. And remember, again, that's 0 to 255. So that's 256 addresses available on that Class C network available to us. So serial days, we are limited to 32 devices a lot of times. There is still a limit to what we can do in the Ethernet world. And if we're on a Class C subnet, we will be limited to 256 nodes on that network. So last slide on the Ethernet discussion, and this is basically to talk about some of the protocols. So another common misconception perhaps is that, okay, if it's all on the Ethernet cable, this is all going to talk to each other. And that is wrong. Furthest from the truth, I was going to say there. Just like anything else, we have protocols that work on the Ethernet network. So again, the Ethernet networking, that's the kind of the physical layer. The wires and the switches and the topologies. We still have to have a protocol that kind of gets transmitted on that physical layer. So in the industrial world, we have a few different industrial Ethernet protocols that are pretty common. There's EtherCAT, or Ethernet for Control Automation Technology. There's Ethernet IP, which is the Rockwell Automation kind of protocol. Profinet, which is, again, Siemens. Profinet stands for Process Field Network. Modbus TCP, so our good pal Modbus, back from the serial discussions, does have a Modbus TCP version, and very much like the serial version, the Modbus TCP IP is a very universal language, once again, or universal protocol to connect a bunch of things together. And OPC and OPC UA, or OLE for process control, is what the OPC stands for. We're seeing that become more and more popular in the industrial space as well. So the Ethernet standard, Ethernet kind of started again to become a standard, shall we say, in the in the 2000s, not late 2000s, but in the early 2000s, really we start to see the tide turn to Ethernet networking. And like we said at the beginning of this discussion, it was a very common networking topology, had a lot of flexibility. It's also the same topologies and networks that the IT people are aware of. So again, it's kind of a consistent networking approach from both your OT, operational technology, and your IT, informational technology sides. And many of these guys above are open standards. So unlike the serial days, the Allen Bradley serial protocol would have been proprietary, or the Siemens serial protocol would have been proprietary. In these cases, these are all open protocols. So any manufacturer can develop on Ethernet IP, or any manufacturer could develop for Profinet or Modbus TCP or OPC, and therefore a non-Rockwell product could be talking Ethernet IP, and therefore can talk to Rockwell. Same thing with Profinet. So that gives, again, a lot of flexibility to the plant floor and to the operators to not be tied to one vendor, perhaps to put a complete control system or control solution together. All right, so that was a lot to cover on the Ethernet side. Our next video will be on the media aspects of Ethernet.